one of the most elusive particles ever known. They're called neutrinos, and they're absolutely everywhere.
It sails out at very close to the speed of light.
3.7 billion years later, they reached Earth.
The scientific community is about to be flipped upside down when experts at Europe's CERN Large Hadron Collider rush to double-check their work in an experiment that appears to have violated modern physics laws. Scientists working at the facility revealed that subatomic neutrino particles may have gone faster than the speed of light through the 17-mile, 27-kilometer long particle collider. The only problem is that nothing can travel faster than light. What is the latest shocking discovery, and what does it mean for the world of physics? Stay with us until the end to learn all about this bizarre discovery. Albert Einstein, the father of modern physics, developed his special theory of relativity on the fundamental law that nothing can move faster than the speed of light, 299,792,458 meters per second. If the experiment at CERN turns out to be accurate, then Einstein's theories, which have laid the way for innumerable technological achievements in the last century, may only be scraping the surface of a far more complicated physical nature of our reality. In recent decades, quantum physics, or the science of reality at the subatomic level, has spread new and fascinating notions, such as the presence of wormholes, multiple dimensions, and the possibility of time travel. Indeed, the entire goal of CERN's research is to collide particles at high speeds in order to eventually isolate and verify the existence of the Higgs boson particle, sometimes known as the God particle. This is thought to be the smallest particle known to exist. It has been hypothesized that this particle may carry clues as to the precise nature of the strong force, which is defined as an extraordinarily powerful attraction force that works on the subatomic level to keep together particles of the same polarity that might otherwise repel one another. Think magnets repelling one another. However, in their quest of the Higgs boson particle, these researchers have achieved a slew of other astounding results. CERN, for example, isolated antimatter for 1,000 seconds only a few months ago. This recent discovery, on the other hand, is much more groundbreaking and might pave the way for previously unimagined technology, because anything that travels faster than light can theoretically breach the time barrier. The researchers who made the discovery are now seeking peer evaluation of their data before formally asserting that it is correct. The feeling that most people have is this can't be right, this can't be real, said CERN spokesman James Gillies. The neutrino beam in issue was measured to be traveling 60 nanoseconds faster than the speed of light, with a margin of error of only 10 nanoseconds. Changqi Zhang, a neutrino physicist at New York's Stony Brook University, believes the result is a consequence of a systematic error. The challenging part, according to Zhang, who is the US spokesperson for a comparable experiment in Japan called T2K, is correctly timing the time between when the neutrinos are born by slamming a burst of protons into a solid target and when they actually reach the detector. That timing is dependent on the global positioning system, and GPS readings can have tens of nanoseconds of uncertainty. I would be very interested in how they got a 10 nanosecond uncertainty, because from the systematics of GPS and the electronics, I think that's a very hard number to get. No previous observations clearly rule out the outcome, according to Kostelecki, who has spent the last 25 years constructing a theory called the Standard Model Extension that accounts for all possible sorts of special relativity breaches in the setting of particle physics. If you had told me that there was a claim of faster than light electrons, I would be a lot more skeptical, he says. Previous measurements limit the possibilities for neutrinos, he claims. Nonetheless, Kostelecki reiterates an old adage: extraordinary claims necessitate extraordinary evidence. Neutrinos are among nature's most enigmatic particles, capable of traveling through the Earth as if it did not exist. Every second, over 100 trillion neutrinos pass through your body completely harmlessly. The fact that neutrinos do not interact with other particles very frequently makes detection challenging. But this does not imply that they never interact. The likelihood of any individual neutrino interacting with another particle is simply very low. They have no interaction with the strong nuclear force that holds atomic nuclei together, but they do with the weak force that regulates radioactive decay. Ultimately, this is how neutrinos are created. For instance, the Hadron experiment found the neutrino mass originating from the disintegration of tritium isotopes. Although many neutrinos were created in a fraction of a second after the Big Bang, many neutrinos are continuously produced today. They arise in the nucleus of stars, particle accelerators, and atomic reactors, as well as during supernovas and radioactive decay of substances. Despite the fact that neutrinos have proven to be difficult to study, physicists believe that neutrinos outnumber protons in the cosmos by 1 billion to 1. This is due to their ability to be neutral to the vast majority of chemicals in the universe, allowing billions of them to pass undetected through a square centimeter of your body. Scientists had already trapped neutrinos prior to the LHC's discovery. The Super Kamiokon detector from Japan, the Mini Boon detector from Fermilab, and the Antarctic Ice Cube detector were all present. They were all able to detect neutrinos using a technique known as Cherenkov radiation. This Cherenkov radiation technique works in the same way that an aircraft exceeding the speed of sound produces a sonic boom. The particle is intended to pass through a material that slows light, leaving behind a faint blue glow that scientists are looking for. About 47 million light-years away, the heart of a black hole-filled galaxy termed NGC 1068 shoots out streams of neutrinos, the elusive ghost particles that haunt our cosmos while leaving little trace of their existence. Bundles of these intangible pieces explode through the cosmic void as soon as they exist. They speed by visible stars and areas of space packed with wonders we have yet to uncover. They continue to fly for an indefinite amount of time until on rare occasions they reach the south pole of the Earth and burrow deep there. The neutrino's journey is uninterrupted. Scientists, on the other hand, patiently await their arrival. Nestled into about 1 billion tons of ice, more than 2 kilometers, 1.24 miles beneath Antarctica, lies the Ice Cube Neutrino Observatory. Ice Cube will continue to keep a watchful eye out for any neutrinos that may bring their group to the icy continent. The worldwide team behind this complex experiment confirmed evidence of 79 high-energy neutrino emissions coming from around where NGC 1068 is located in a publication published November 3rd in the journal Science, opening the door to novel and endlessly interesting sorts of physics. Scientists refer to it as neutrino astronomy. Until now, physicists had only seen neutrinos originating from the Sun, our planet's atmosphere, a chemical mechanism called radioactive decay, supernovas, and a blazar, or hungry supermassive black hole pointing directly toward Earth. Due to Ice Cube's initial success in 2017, a void named TXS 0506+056. With the discovery of this new neutrino source, we are entering a new chapter in the history of the particle. According to the research team, neutrinos originating from NGC 1068 may have millions, billions, or even trillions of times the energy of neutrinos originating from the Sun or supernovas. Those are astounding figures, since in general such phantom particles are so powerful but evasive that trillions upon trillions of neutrinos pass through your body every second. You simply cannot tell. And if you wanted to stop a neutrino in its tracks, you'd have to combat it with a 1 light-year wide block of lead, and even then, you'd only have a minuscule chance of success. Thus, whether we use NGC 1068's version or not, harnessing these particles could allow us to explore portions of the universe that are normally out of reach. This moment is significant not only because it provides more evidence of the mysterious particle that was not even discovered until 1956, but also because neutrinos are like keys to our universe's backstage. They have the potential to expose phenomena and answer mysteries that other methods cannot, which is why scientists are working to build neutrino astronomy in the first place. The universe has multiple ways of communicating with us, Denise Caldwell of the National Science Foundation, a key funder of Ice Cube, told reporters on November 2nd. Electromagnet radiation, which we see as light from stars, gravitational waves that shake the fabric of space, and elementary particles such as protons, neutrons, and electrons spewed out by localized sources. One of these elementary particles has been neutrinos that permeate the universe, but unfortunately, neutrinos are very difficult to detect. In fact, despite years of scientists attempting to break its curtain, the galaxy NGC 1068 and its massive black hole are often shrouded by a thick veil of dust and gas, making them difficult to analyze with normal optical telescopes and equipment. Because of its infrared vision, NASA's James Webb Space Telescope may have an advantage in this scenario, but neutrinos may be an even better way in. These particles, which are expected to be generated behind such opaque screens that filter our universe, can carry cosmic information from behind those screens, zoom across great distances while interacting with essentially no other matter, and deliver pristine, untouched information to humanity about elusive corners of outer space. It's also worth noting that there are many, many more safer galaxies comparable to NGC 1068 than there are blazars similar to TXS 0506 plus 056. As a result, IceCube's latest discovery is perhaps more significant for neutrino astronomers than the observatory's original one. Perhaps the majority of neutrinos circulating across the universe are generated from NGC 1068 doppelgangers. But in the larger scheme of things, neutrinos are considerably more valuable than their sources. What are your views on the most recent discoveries revealed regarding neutrinos? Share your thoughts with us in the comments section below.